Welcome everyone, and in this first video we are going to talk about complex numbers. So this is the first part of this course and we want to look at problems like this. So essentially let's think of this sort of thing that we want to talk about x square plus 1 equals to 0. This is a quadratic equation, as you know, right? And of course this quadratic equation has no real root, right? Because you see it will be x square equals to minus 1 and there are no real number x, so there does not exist a x in R such that 1 has a solution. This we already know has a solution. Yes. Okay. Now the question is this. So can we extend somehow our understanding of this real number such that these sort of equations also have roots? Okay, so why do we need it? So think about it this way. Let's say you have this natural number set, right, which is like 1, 2, 3, this set. Now on this set, if you are thinking of this sort of equation, x plus half equals to 0. This is also an equation, right? Yeah, I may ask you what is the value of x, and in this case you can say x equals to minus half, and that is a valid number. X equals to minus half, that is a solution of this equation, right? Okay, but the thing is this. See, this minus half does not belongs to this natural number set n, right? So you see this equation does not have a root in this system n. Okay, so that is why you see what we did is we extended this natural number to something called the rationals, right? And in that rational set you have a root of this equation. Now of course you can also look at this problem as x plus pi equals to 0. Yes, and then you will get a solution x equals to minus pi, which is again irrational number. So you do realize this rational set in some sense is not even enough to actually take care of all solutions of this sort of thing. So because in this case x is irrational. So we extend this set more and more and we talk about real number. What is real? So essentially this is by our definition it is the rational union the irrational. Clear? And in this set more or less most of the problems which we generally handle up till now were working. So essentially you have this sort of problems. Let's say x square plus 2x plus 1 yes equals to 0. So that's a quadratic, and you can solve this quadratic. What are you going to get? You are going to get x equals to minus 1. Yes, and of course minus 1 twice because of the multiplicity, but you are going to get a real solutions out of it. That is fine. Now, but again, we know that if we change it a little bit and the problem looks like x square plus 1 equals to 0, in that case you do not have a real solution. Now, going by the same idea, can we extend this set? That's the question. Yeah, can we extend this set such that this sort of problem also, because there are lots of other problems also, right? You can see, let's say this equation x square minus 10x plus 40. You can check out that this also doesn't have a solution in a real line. Yes. So what do we do now? So to account for that sort of thing, we introduce, okay. So we start by introducing something called a complex number. So this is a complex number, okay. So in the first part of this video, I am not going to talk about everything very precisely. It's just to give you an idea of what exactly are we trying to do here, okay. So essentially, we are not going to look at just one number anymore. So you see, real number, we just write it like a single tuple, right? Here, what we are going to do is we are going to write it in terms of a two component part. So what we are going to do is we are going to talk about a complex number z. So this is the notation which I am going to use throughout the whole course. So z. So whenever I say z is in C, this is C. C is what? C is the set of all complex numbers. So this is actually the set of all complex numbers. All complex numbers. Okay. Let's just understand what is z now. How do we define z? What are complex numbers? See, I wrote C is a set of all complex numbers, but I did not define what a complex number is. So now I'm going to define it. So z will be defined in terms of two components. The first component is x and the second component is y. Clear? Okay. See, what are these x and y? Now, what do we know up till now? We know what are real numbers, right? This is what we know. So we are going to use this real number to define something called a complex number. Okay. So what we are going to do here is this. See, z we are going to define it as x and y, that's the component, and where x and y, I mean individually x and y, these are in R. So basically you take a real number, you take another real number, put it together in this sort of ordered tuple, no? You cannot change this ordering, and then you are going to get a complex number. Clear? Okay. So now in this case, what happens is the first component which I am going to get, we are going to write this first component x as the real part of z. This is just a nomenclature what we are going to do. It's nothing to do with, complex number first of all is not complex. It is not like something imaginary number what you say generally. I mean, don't think of it as a something out of the, blue. It's not something like that. Real, this is just a nomenclature. Okay, z, the first component x is, we are going to call it a real part of z. Real part of z is just a nomenclature. Okay, and this y, you see the second component y, this we are going to call as the imaginary part of z. So this is called the imaginary part. There is nothing imaginary about it, but we are going to call it like that, of z. Yes, these are as real numbers. See, complex numbers are as real numbers. Yes, but the thing is, we are just going to put it this way, that this is a complex number. Okay, right. So let's look at what we can do with this thing. So how does all of this work? So essentially what we are doing is this. See, if you think about it this way, you see, initially when we were talking about q or n, see, when we go from n to q, you see, we are taking n and we are adding some more elements to it, and we are getting q. And again, when we are going from q to r, we are taking q and we are adding more elements to q, and we are going to get r, right? Okay, and then now even R is not enough for all our solutions. So what we are going to do is, we are going to take R and we are going to put some more elements in it, and we are going to end up with C. That's the idea. Okay, so somehow C should contain all element of R. That's the general idea. Clear? Okay, so first of all, let us just understand one very simple thing. By definition, this is by definition. Let's say if I am saying if z1 equals to z2, if I am saying this thing, that will imply, this is by definition. So if z1 equals to x1 plus iy1, okay, sorry, let me write it this way, x1 and y1, and z2 equals to x2 and y2 equals to x2 and y2, then z1 and z2 equal means x1 is equals to x2 and y1 and equals to y2. This is simultaneously, both of them has to be true. Clear? So the real part has to be same and the imaginary part has to be equal, right? And also you see the imaginary unit. See, there is something called the imaginary unit which we are going to call, so 0, 1, this one. The first component is 0, the second component is 1. This is a very, very special number in our complex plane. So this number, we are going to call it an imaginary unit. And this, we are going to denote. We are going to put a very special notation for this. So denote, and we are going to denote I. I as this 0 and 1. Okay, so what we are going to do is, essentially we started with a real number and then we are putting two real numbers together in a tuple x and y. And then what we are going to do is, for x equals to 0 and y equals to 1, okay, this particular tuple, we are just going to call it an imaginary unit, which is I. Okay, I is just a notation, nothing special is going on here, it's just a notation. Okay, so now what we are going to do is, we are going to define. So once we have this I, we are going to define some addition and multiplication, because you see, in n and in r we know how to add and multiply two numbers. So here also we must know how does it work. So addition, how does it work? Let's just understand this thing. Addition. So let's say that I'm always going to define this thing. X1, whenever I'm writing, you just assume x1 plus iy1. We are always going to assume this thing. Sorry, x1 y1. Let me write it this way. It will be better. X1 y1, the two tuple x1 y1, and z2 is x2 y2. Clear? This is how we are defining it. And then what we do is this. See, we are going to define addition. So Z1 plus Z2. Let's just define this thing. Yeah. So define, this is definition, Z1 and Z2. How are we going to define it? We are going to take the real parts of Z1 and Z2, and we are going to take the imaginary part 1 of Z1 and Z2, and we are going to add it together. So what we are going to do is, real part of Z1 is X1, real part of Z2 is, so essentially we are going to do something like this, X1 Y1 plus X2 Y2. Yes. So we will define it like X1 plus X2, X1 plus X2, and Y1 plus Y2, Y1 plus Y2. Yeah, that's our definition. Okay, and very simple. This is the similar sort of definition which you do in R2 also. So in R2 also you have similar sort of set, right, which is a set of R cross R. So essentially you take a real number, you put another real number just in a component wise, and you define addition like this. Yeah. Now here comes the important bit. This is called multiplication. Okay, and this is very important. Why I am telling you? Because this is what actually separates out R2 and C. Okay, because otherwise you will see that essentially R2 and C are essentially the exact same thing in terms of set and all. Doesn't have a different elements, but the thing is how the element interact with each other is different. So here we can, for C, we take Z1 times Z2. This we can define. Yeah, and how do we define it? So this is a very special definition. So essentially what we want to define is X1 Y1 times X2 Y2, X2 Y2. Okay, and if you define this thing, we are going to define it like X1 X2 minus Y1 Y2, yeah, and X1 Y2 plus X2 Y1. This is just a definition which we are going to use. Yeah, and this is always true. I mean, in terms of whenever we say something, somebody says about a complex number, this definition always holds. Yeah. Now, this is what I told you is this. See, this definition is what differentiates R2 with C. C is essentially, if you think about it, it's basically you take one for the first component real number, the second component real number, this sort of thing. And R2 is also similar sort of thing. So as I said, they are essentially same elements. But the point is this, even addition, if you look at it, you see in complex addition also and real R2 addition also exactly same rule works. Yes, but multiplication, if you see, let's say if you have a two vector, yeah, let's say x1 y1 is a vector and x2 y2. So x1 y1 is a vector and x2 y2 is a vector, right, in R2. So these two elements are in R2. Now if I ask you that can you multiply these two elements, okay, so can you multiply two vectors? You can't. So this is not defined. Clear? That multiplication is not defined. Yeah. Now you can talk about, of course, there is something called a dot product, but dot product is not a true multiplication, because when you do dot product between two complex numbers, what you are going to end up is with a real number. Yeah. What we want to do is we want to multiply two things, but we always want to end up in C only. In the same set only. Then multiplication makes sense. So in this case, what happens is you do realize what is the difference between R2 and C. The thing is the multiplication, this particular operation. Multiplication operation, this is what differentiates. So let me write it. This is the main differentiator. It is not your usual differentiation. This is differentiator in means what is the difference between these two. Differentiator between R2 and C. See, essentially what we have is this. We have both the set. As I said, they are basically same. But the thing is the operation which you are defining are totally different in this. The addition is same, but the multiplication is different. Now the thing is, whenever you are defining a concept based on this addition and multiplication, if you are defining a concept based on just addition, those concepts are same for R2 and C. But the thing is, if you want to somehow include multiplication there, or then it changes. Okay. Now with these two definitions, what we have, let's see. You see, if you have two elements, maybe let me put it a small remark. If you have two elements, Z1 which is x10, and Z2 which is x20, x2 and 0. So you do realize what is Z1 times Z2? It is x1 x2 times 0, x1 x2 and 0. You can just put everything here and you can check. So please check this part. You can check this and it is 0. Okay. Now you see here what happens is the complex numbers, this extends the real number, right, in some sense, because you see here what happens is the imaginary part is 0, and we say, so since the imaginary part is 0, you can think of this as basically an extension of real number. Clear? So essentially you see x0, what is it? This is x. Yeah? You can think of this sort of extension. The imaginary part, there is nothing. So in that case, you can just identify this complex number with a real number. Okay, right. Now you see what we can do. Another very important thing is this. So in this case, this is what we are trying to say. See, this actually, I mean, you can think of that the complex extends the real. Complex number, basically number extends the real number. Okay, right. Now let us look at the, so this is remark 1. The second remark, let's say I have I want to talk about this particular thing, 0y. Let's just say, yes. See, 0y, if you want, you can write it as 0 times y, okay, minus 1 times 0, yeah, and then 0 times 0 plus 1 times y. Yeah, this is just I mean, some funny way of writing it, but essentially what happens is this becomes 0 1 times y0. Clear? Yeah, I mean, if you can always see that this is basically 0 1 times y0, and as I already told you, 0 1 is our imaginary unit, right? It's a very important part, and this we define it as I. So this is nothing but I times y0. Clear? Yeah, and so we write it as I times y. Yes, so this is kind of, you can think of it like this. See, let's say y is in R, right? Think of it like y in R. Yeah. Now, if I is in C, yeah, I is in C, this we already know. So what is I? I is 0 and 1. Okay. Now, if you want, you can write it like this. You see, we write it like I times y is what? It is essentially 0 1 times y. Clear? Huh? And this y, see, this is a real number, and real number we can think of it as a complex number, right? So extension of a complex number, which we already talked about in remark A. So think of it y as a real number as y times 0. Yeah. So that is nothing but this one, you see. Yeah. So you see, 0 times y, you can actually write it times I times y. So this is how I is getting incorporated in the whole particular context. Okay. Right. So now what we want to do is we want to talk about another very important topic, that how to write down a complex number. So in practice, how do you write it? Generally speaking, remark C, generally, okay. See, Z is a complex number which we write it as x times y. Clear? Now, you see, you can also, if you think about it, you can write it as x plus I times y. Yes, because you see, I times y we already talked about, it is 0 times y. You see, this, you can think of it like this, right? x0 plus 0y. Yes, x0 plus 0y, we can write it like this according to the addition of complex numbers. x0 remains x0, and 0y, if you see this, you can think of 0y, you can think of as I, right? And this is your basically x0 is the imaginary part is 0, so that is your real number 0. So essentially you are adding x plus I times y. So that is how we write xz, which is x and y, as x plus iy. Okay, of course, with this notation, what happens is this. So D, the remark D. Now you see, if x equals to 0, yes, then z, what happens? This becomes I times y. So essentially you start with z, which is x plus iy, yes, and then if I am taking x to be 0, then z turns out to be I times y. Clear? And then what happens is, so what essentially is I? You see, I is nothing but 0 and 1. Yeah, so that will imply I times I, which is I square. Yeah, that will be 0 1 times 0 1 times 0 1. Yeah, and then when you multiply this thing, this actually, according to complex multiplication, will give you minus 1. So essentially, I is such a number that I squared is going to be minus 1. And hence, you see, with this idea, you get, so we wanted to solve this problem, right? X square equals to minus 1. See, with this particular idea, we actually get the solution x is equals to I and minus I. Yeah, because you can see that if I'm changing I to minus I also, the similar sort of thing works. Okay, so we can have this problem. Okay, so up till now is fine. any complex number, how we can write it? Z can be written as x plus iy. Yes, and if you want to talk about addition and multiplication in this, so how do addition and multiplication again in this? So in this term, how do you write it? Very simple. X plus iy, if we want to write it, yeah, it becomes x1 plus x2 plus I times y1 plus y2. Clear? Yes. And so this is the addition. If you want to do it in terms of, if we start with I, then we write it like this. And again, x, sorry, I made a small mistake. Yeah? Sorry. This is x plus y. Okay. And x, I am taking it to be x1 plus iy1 and y to be x2 plus iy2. Okay, and then x plus y, if I am just adding two elements of complex numbers, I am just adding x plus y, and that by definition is x1 plus x2, the real part, plus I times y1 plus y2. Yes, you can check using your definition also. So again, let's say if I have this sort of thing, x1 plus I y1, so this is your x, and then you have y, which is x2 plus iy2. Yeah, if you take the multiplication of those two, then what we are going to get is x1 x2 minus y1 y2, okay, plus I times x1 y2 minus x2 y, sorry, this is plus y, x2 y1. Yes, so that is how we are getting in terms of I. That is the only idea. So up till here, it is very simple, and I'm quite sure all of you guys know how to handle these things. Yeah. Now what we do is, this is the last part of this video. We are only going to talk about subtraction and division. So the inverse operations, subtractions and divisions. Now you do realize, once I define addition and multiplication, subtractions and divisions are the most natural thing to work with. And what do? We just do it like this. See the difference. So let's say z is any complex number, and it is equals to z1 minus z2. z1 minus z2. Okay. So and z1, so that we are going to define it like this. See, x1 minus x2 plus I y1 minus y2. Okay, where z1 is x1 plus I y1 and z2 is x2 plus I y2. x2 plus I y2. Okay, so in that case, what is z1 minus z2? z1 minus z2 is x1 minus x2 plus I y1 minus y2. Exactly the similar sort of thing which we can do with the combining the addition and multiplication. Okay, so this is combining both addition and multiplication. Combining addition and multiplication. Okay, if you are not convinced, I will ask you to please go through it, how to get this part. Okay, and then we are also going to define something called a division, right, which is the quotient. So the quotient, this is A, and the quotient which we are going to define is, so this is the difference essentially, yeah, difference, and the quotient is this. You see, Z, we will define it to be Z1 by Z2. Okay, and of course we will again assume Z2 is not 0. This is the similar sort of thing in real number also. We don't want it to be undefined. So essentially Z, which is Z1, Z2, so that will also give you a complex number. Okay, so even if you can divide two complex numbers except not by 0. So what is 0 here? See, when I am writing Z2 not equals to 0, it means that Z2 is not equals to 0, 0. Clear? So Z or 0 plus I0, whenever, whichever you want to write it out. Okay, so both the components are not 0. Yes, so Z equals to Z1 and Z2, and that is a complex number which we are saying this is defined. Yeah, see, for this, what happens is Z1 will become Z times Z2. Is this okay? Yeah, and if you write it down, you see, if you write Z1 to be x1 plus iy1 and Z2 to be x2 plus iy2, then you see from here, and xz to be and z to be, so z is x plus iy. Yeah, Z1 is x1 plus iy1, Z2 is x2 plus i2. So in this case, what happens is, because these two complex numbers are same, what happens is x1. If you take the real and complex imaginary part, so x1 becomes x2x minus y2y, and y1 becomes y2x plus x2y. Clear? Now what happens is, if you find, if you solve for x and y, what we will get is your solution, which is z, which is x plus iy, of course, and then x you will get it as x1 x2 plus y1 y2 by x1 x2 square plus y2 square. This is non-zero, so this is defined, plus I times, yes, the second part, the imaginary part, which is x2 y1 minus x1 y2 by x2 square plus y2 square. Yes, I hope this is clear. So this is how you define the quotient between those two numbers. Is it okay? Yeah. And a practical way of looking at it is, so think of it like this. See, z is nothing but x1 plus iy1, x1 plus iy1 and x2 plus iy2, right? So we write it like this: x1 plus iy1, and you multiply it by x1 minus x2 minus iy2. Okay, you multiply it by this, and then in the denominator you have x2 plus iy2 and x2 minus iy2. If you multiply these two, you will get a x2 plus y2 square, x2 square plus y2 square. This is the part, and then you do multiply this, you get the numerator. So this is how you can do it, and of course you more or less, I am quite sure you guys know this part. So with this, I am going to end this video. Thank you.